recording, so at least I don't forget that. And I'll start a chat session. And if students, by the way, as far as I know, the only image of a human being, or even the only black square that might be a human being, is the one with my face on it. Isn't that right? In other words, the square with all the rectangle with all the rectangles for the students is never on screen, right? And so consequently, if you want to appear with your own names and faces, I think that's okay. You can all see this screen, the screen with the book and the examples and so forth. I put the hydrogen atom example on as an example on the examples document. These documents that are on the class web page, instead of having a new document every time I add something, I just add something to some of the documents. When they get too long, I start a new document. But examples now has 47 pages, and some of the class notes, they start on some date, but go on for several days. Okay, so we've got to start officially now. Does anybody have a question? It's always good to deal with questions to begin with. All right, I don't hear a question. Let me clarify something that I skipped over, I think, too quickly a couple of nights ago, or last time I did it. And it has to do with symmetries and conserved quantities in field theory. So one part that I went through, I think I went through pretty carefully, and that's okay. But I think the part for space-time is a little bit different. You see, what you do over here is you say that an action density is unchanged. If a symmetry is of a Lagrangian, or an action density is one in which one kind of symmetry is one in which the action density is unchanged when the fields change by a certain amount. So the fields change by delta phi, and their derivatives change by the derivatives of delta phi. And so you then say that there's no change in the action, therefore this quantity vanishes. You then apply Lagrange's equation, you get that this current has no divergence, and that gives you a conserved quantity. The case of space-time invariance and under space-time translations is a little bit more subtle. And the idea there, so I've rewritten this, the idea is that if an action density or Lagrangian depends on the space-time coordinate xa only through the fields and their derivatives, then the derivative of L is this. Then you use Lagrange's equations to write partial L partial phi I as d by dB of d by dxb of partial L with respect to the xb derivative of phi I. And then you can combine these two terms, and you can combine this one with the aid of a delta function, and you then construct the energy momentum tensor of the theory. And that then has zero divergence. So which energy tensor, which thing has zero divergence? It's the energy momentum tensor for A. In other words, the invariance was L doesn't depend on XA. A can be 0, 1, 2, or 3. And then the momentum PA inside the volume is equal to the flux coming through. If the action density has no dependence on any of the space-time coordinates, then energy momentum are conserved. So I hope that makes that a little clearer. Are there any questions about this, perhaps? All right, so let me skip then to the next topic, which was integral equations. And we went through the basic things about these. They're basically what you basically do is you take your differential equation, first order linear differential equation, you integrate it, and then you use Cauchy's trick, and you get to write it in this form. And so you then have, for the Fredholm case, you have basically this form here. This is called the kernel. And what you're given F, and you're given the kernel coming from integrating the differential equation and applying Cauchy's trick. Once you do that, you then get an integral equation of this form. And the nice thing about integral equations are that they are mathematically, the integral smooths out singularities, so you can deal with the equation. You can apply various theorems to the equation. And moreover, it expresses things in a way that makes it obvious how to solve the thing numerically, namely that you just divide the interval between A and B into 10 or 1,000 or 1,000,000 or 1,000,000,000 points, and then you have a linear algebra problem, which you can just ask MATLAB to solve, or you can use Fortran to solve it. The Volterra equations differ just in that if the kernel is causal, that is to say, it's non-zero only when x is greater than y, then it's called a Volterra equation. That's just a special case then of a Fredholm equation. And because of the linearity, you can add solutions. The general solution of an inhomogeneous integral equation is a particular solution, the inhomogeneous equation, plus the general solution of the homogeneous equation. And then if you, as I said, if you discretize space, the interval, it's not all of space, it's just an interval, you then can convert. Let me make this bigger so everybody can see really clearly. You then can convert this integral equation into this linear algebra matrix equation, and bingo, you get solutions. This, I think maybe I went a little bit too far with the pseudo inverse there, but you can read it in detail if you want to. Now, this business of integral equations, this is a little bit sophisticated, but I think it's sufficiently general, and it kind of unifies. It'll unify your thinking. So the idea is we have some function u of z, say, and some differential operator that differentiates with respect to z. So we've just jumped to the complex plane just because we found that if we go to the complex plane, we're somehow better off. Anyway, so z is x plus iy, and we're given L and C, and we're trying to find U. C is a constant here. And so the trick is to say, well, we're going to write this as an integral equation. And what we're going to do then is write it in this way. So now what we're doing is we're expressing U as an integral of a known kernel and some unknown function V. Once we know V, we'll know U. And the idea is that we have to choose K so that this K is equivalent to that. So the first is a choice of K, and there's a choice of a contour. The next thing is another choice. So there's a lot of freedom here. You choose a when you apply the operator L to U. So here what we're doing is we're just representing the unknown function in terms of a second unknown function and a kernel that we've just invented. And if we say that U is this an integral along a contour in the W plane of K times V, then we take this and substitute in there. What we've got is that L on U is just L on this, and that's LK. And then the CU is plus CK, all multiplying V, integrated along the contour equals 0. Okay, so far we've just translated this. We've just represented U in this weird form that's incredibly general because K is general, K is arbitrary, C is contour is arbitrary. So there's just enormous freedom here. The next step is we find a linear operator M that acts on the kernel with W derivatives, and that gives L acting on Z. I'm sorry, L acting with Z derivatives. Actually, I think this is actually slightly wrong. This should be Z derivatives. So let me change that to Z. I rewrote this afternoon, and whenever I rewrite something, why is it called a kernel? I don't know. It has nothing to do with Kentucky Fried Chicken, and it was, I think, terminology that some German mathematician invented. So what we want to do is we find a linear operator M that acting on K with W derivatives gives the same thing as L acting on K with Z derivatives. And I see I've got more stuff. K acting, all right, hold on. Let me just get rid of some more of this stuff. All right, so now I think I've finally rewritten it correctly. It's not wrong in the book. I just think this is a little bit clearer. So we want to find a linear operator M that acting on K with W derivatives is the same as L acting on K with Z derivatives. So this is what we've got. Then we get this integral equation in which what we've got now is W derivatives that we can integrate by parts. And we can choose the contour C so that when we integrate by parts, the boundary conditions vanish. How do you choose a kernel? In this method, you have total freedom and you just have to do it appropriately. And so it's a question of imagination, luck, taste. I don't know what else, but let me give you a couple of examples. And all right, you might wonder, why go through this hell? Well, it turns out that when you do, you can take a differential equation that's a nightmare and convert it into something that's very simple. And so, for example, one kernel is e to the I zw, and that is expressing an unknown a function u in terms of its Fourier transform. Another one is e to the minus zw, that gives you a Laplace transform. The kernel z minus w raised to some power a occurs in applications of Cauchy's integral theorem and integral formula. Clearly, because in other words, it's let me just maybe make this. I have to lean over this to get. All right, let me see if I can switch to maybe red. Okay, and let me see if I can make this somehow visible. All right. So the idea here is that f of z, for example, is an integral f of w dw over 2 pi I w minus z. So let me maybe go here with a little bit of, all right. Okay, so what you see here is that this is the kernel w minus z to the minus 1. So what we see here then is that a whole raft of mathematics, Fourier transforms, Laplace transforms, Cauchy's integral formulas, are all examples of this general technique of integral transformations. And one example of their utility is Bessel's equation, which we'll get to in another chapter in maybe next week. Bessel's equation is a second order linear differential, ordinary linear differential equation. L is then this structure here. The constant C is minus lambda squared. And what we do is we choose M as a second derivative with respect to W, and we seek a kernel K that does this. So what we want is that minus K, minus the second derivative with respect to W, gives you Z squared, second derivative with respect to Z, first derivative, and K. And the kernel that works is e to the plus or minus I Z sine W. So you take this K and stick it in here. So you take this exponential and put it here. Take this exponential, differentiate with respect to Z and put it here. Differentiate twice with respect to Z and put it there, and you want that to be the same as minus the second W derivative of this, and it turns out that this solves this equation here, and it's an entire function of Z and W, and now then we take it and we put it in this previous equation. In other words, that the second W derivative of K plus lambda squared K acting on V should be 0. Since these are W derivatives and we're integrating over W, we can integrate by parts. And if we integrate twice by parts, the prime means W derivative. So I've got kind of a mixed notation. This is W derivative, that's also a W derivative. and integrating by parts twice, we then have a boundary term, but we've chosen the contour so the boundary terms vanish. And then what do we have to make this zero? Well, the only thing we have to make this zero is we just have v double prime plus lambda squared, v is zero. So we've turned this differential equation, which is pretty hairy, pretty hard to solve, into something that's trivial. It's just a harmonic equation. It's just the ye olde harmonic oscillator. And so the solution of this, of course, is v is e to the I lambda w. And so now our unknown Bessel function is an integral of v, which is just e to the I lambda w, times the kernel, and the kernel is this very simple form. So now we've got the most general solution. I think it actually is the most general solution of Bessel's equation as an integral transform. And this works for any contour. We just have to choose the contour so that the boundary terms vanish at the ends of the contour. And if we choose the real part of z positive, and have any complex lambda, we can choose contour C1 that runs. So let me show you what C1 looks like. C1 runs from minus infinity, minus I infinity, up to 0. And then it goes to minus pi. And then it goes up to minus pi plus I infinity. Damn. So this is minus pi plus I infinity. So this is the contour. That's that contour. On the other hand, there's another contour, and the contour that you get then is you just integrate this along that contour, and this is called the first Hankel function after Hermann Hankel. So these are the Hankel functions. Well, he only lived 44 years. My goodness, 34 years. Wow. Very productive guy. Anyway, the second Hankel function is defined for real z positive. So the first one was also real z positive. Oh, let's see why the boundary terms vanish for real z positive. So real z is positive, right. And so we have W is huge and positive imaginary, say, and that means, wow, all right, this is a little complicated. So let's just say that the boundary terms vanish. I think that's a good homework problem, but not one to do immediately in class. The second Hankel function is the same thing almost, but a different contour. And now we have a contour that runs from pi plus I infinity to down to pi, and then to 0. And then lastly, down to minus I infinity. So on these, so that's the contour for the second Hankel function. And notice that this is an entire function of z and w, so you can deform these contours and analytically continue the Hankel functions beyond the right half plane. Right half z plane. So I should have said z plane. And you can also show that the two Hankel functions are complex conjugates of each other when lambda and z are both real. All right, I think that's enough for this topic. It's okay, there's a big question here. Example 7.56, okay, hold on. I'm just guessing, I don't know where it is, example 7.56. Oh my goodness, that's 7.45. Whoops, I've gone much too far. All right, I'm trying to find example. Can you tell me what section it's in? Example 7.56, because I just don't know. So anonymous, please tell me what section is, okay, 743. All right, so that's easy to find then. Whoops. Oh, we're almost there. Okay, 7.56. Okay. Okay, so the Green's function of the Helmholtz equation must satisfy that. By using the Fourier transform, we show that the Green's function is this. The Green's function of the modified Helmholtz equation is that. Okay, I have which equation are you talking about when you say upper and lower indices on the partial differential operators? I don't see any indices on partial differential operators. Oh, okay. That's right. Damn it. I've added examples, and so things are screwed up. So we're looking at this example. We're talking about example 7.57. Okay, well, let me answer the question more generally rather than just by. So let me switch to a different color. Let's go with black. Whoops, black. Okay, here's the deal, to quote Biden. T is x0, minus t is minus t is plus lowercase x0, which is minus uppercase x0. And of course, when I say sometimes one really means that t is x0, sometimes one means that x0 is ct. So whether you have a c here or not depends on your units and conventions. But on the other hand, x is with ordinary coordinates. This is x1, and that's the same as lower x1, Y is x2, which is the same as lower x2. Z is x3, which is the same as lower x3.
Dr. Cahill, that's the wrong example.
Oh, Christ. Thank you.
I would send you a picture of it, but the chat function doesn't allow me to do that.
Right. Well, you could turn your video on and get it, show it to me. Yeah, there you go. All right, I'm seeing something. I'm seeing a ceiling, I think. I'm still just seeing a ceiling. Well, now I'm not seeing anything.
Should be two more examples forward. It has the Feynman's propagator, and then it has Green's function with boundary conditions. And then the one we're asking about is theory of a scalar field. Yeah, so the one after this one.
Thank you. So we're talking about an example now, theory of a scalar field.
Yes, that one.
Right, okay. All right, okay, good, great that you asked this question. This is really important to get this straight. And I must tell you, when I was a graduate student, I unfortunately skipped the course in which this was explained. And so I had something of a nightmare trying to figure it out for myself. Moreover, the professor teaching the course, Sidney Coleman, actually, he used the opposite metric. So I had 3 minus signs and only 1 plus sign. So it was worse. All right. So what is dA? This is partial with respect to x upper A. And d upper A is partial with respect to x lower A. That's the convention. Is this an intelligent convention? I don't know, but that's the convention. So, for example, the time derivative, or partial with respect to t, is just partial with respect to x0, but partial, oh, sorry, hold on, let me just rewrite this. And so this is partial sub-zero. And partial with respect to x is partial, of course, with respect to x. And this is partial with respect to x1, and we write this as d1. Partial with respect to y, partial y, partial x2 equals partial 2 and damn it. Oh, these touch screens are sometimes a little too touchy. Partial z now, notice that we have 1 minus sign and it affects the index 0. So this is equal to minus d0. And this is equal to plus d1 equals plus d2 equals plus d3. Another way of thinking about it is that x with a lower index is eta AB x with an upper index. And so what that means then is that you've got minus 1, 1, 1, 1. This is eta. And then you have the x0, x1, x2, x3. And this is x0, x1, x2, x3. Okay. So this is the this is the convention that's used by people doing general relativity and by Steven Weinberg, who wrote the best books on, and articles for that matter, on almost anything, any given subject. The only difference between this notation and another common notation is that some people use, instead of -1 plus 1, they use +1 and then 3 minus signs. And the reason they do that is just because they want p squared to be positive, where you see, for me, p squared is minus p0 squared plus p vector dot p vector. And by p squared, what we mean here is the Lorentz invariant inner product, which is to say the sum a equals 0 to 3 of p lower a, p upper a. And so this is minus p0 squared plus p1 squared. Well, it's upper p1. All right, hold on me. Well, here I can just, there. P1 squared plus p2 squared plus p3 squared. And here I'm using units where c is equal to 1. And so this is minus e squared plus momentum squared. And so this is minus the mass squared of a particle. Now, people who do particle physics and only particle physics like to have know that m squared should be positive. They want p squared to be m squared, so they put in 3 minus signs, and I think they just screw everything up. Okay, I hope that I've made that clear. Oh, let me just add one more thing. What's meant here, because it's a sum over repeated indices, so this is sum b equals 0 to 3 of eta ab x b. So basically you use eta to lower indices and raise indices. And the only effect it has is on the time variable. And the only reason to have it is so that you have, is that if you have 2 4 vectors, x and y, then the inner product here is the dot product of the spatial components minus x0 minus y0. And you can write that as xa, eta ab, yb. So that gives you this. In special relativity, the use of eta is kind of overkill. And in fact, when Feynman often just dispensed with it and just said, you know, you use the minus sign when you need to. And that probably is the right attitude for just doing particle physics. In general relativity, this eta becomes GAB, which is the metric of space-time. And so your invariant distance between 2 points is GAB x a minus ya xb minus yb. And of course, this is summed over AB going from 0 to 3. And so this is the metric of space-time. Okay, so we've gotten all right. I mean, yes. So with regard to the anonymous question there, you can use eta to raise and lower indices, or you can just do it by hand. If it's a time index, you need a minus sign. And if it's a space index, you don't. And the thing to remember is that the ordinary derivative, the ordinary variables, my handwriting is not very good in general, but on a screen, on glass with an Apple Pencil, it's even worse. On ordinary variables, upper index is usual variable. No hidden minus signs. And the derivative, which is partial with respect to x upper A, is ordinary derivative. No hidden minus signs. And the only thing then where you get a minus sign is if you have a lower space, a lower index on an ordinary vector or 4-vector, or you have an upper index on a derivative, on a partial derivative. Then you get a minus sign if you're dealing with the time component. So basically you can say x upper A is the true coordinate, d lower a, which is the derivative with respect to the real coordinate, is the ordinary derivative. Okay, I think third line in the example. This is the example, 759. Okay. Well, d by dx lower a is the same here. This is, if I write this equation 7.46, if I write this equation in complete detail, it's partial with respect to x upper A. Of course, we're summing. A equals 0 to 3. Of the partial derivative of the action density with respect to the partial derivative of phi k with respect to x upper A is equal to partial of L with respect to phi k. K just labels there's no funny sign there. K means, you could leave out K, and I probably should have. So let me get rid of K here because it just would be electron, photon, whatever. So I'm going to get rid of K. Okay, so this is Lagrange's equation for a single field. If you have several fields, you go there. So there, I'm only using upper indexes. And I was here also because you see, this is the derivative with respect to the ordinary coordinates, and this is also the derivative with respect to the ordinary coordinates. In other words, dA is partial with respect to x upper A. So these two derivatives meant the same thing, and this equation could have been written and maybe should have been written. I can even rewrite it if you want. It would be let me just rewrite it here. If I didn't screw anything up, here's the rewritten equation. But this is just, this business with the upper and lower indices and so forth is all just, it's all just notation. It's not actual mathematics, or for that matter, physics. It's just notation that you've just got to become comfortable with. All right, let's go on to the next chapter. And frankly, this chapter is very important and much simpler than the topics that we were just now discussing. And let's see, I think we have a half hour, we can do a good chunk of it. It's all actually, to tell you the real truth, this whole chapter is really very simple. It's just a bunch of polynomials and their definition and some of their properties. So you can expand things in terms of power series. And so you can expand any nice function as a power series or Taylor series in terms of its derivatives. It's 0, x to the n, and so forth. So these x to the n's, they're complete, but they're not orthogonal, and they're orthogonal, and they're not normalized. So what Legendre did was to make them orthogonal and normalized in a particular way. So the first orthogonality relation is this, that he defined for every integer n, he picked an interval from -1 to +1. For every integer n and m, if n and m are two different integers, the integral of the product of the two polynomials has to vanish. So they're orthogonal. And it turns out that that's equivalent to saying that the nth order Legendre polynomial integrated with respect to m vanishes if m is an integer less than n. And of course, what I meant was 0 less than or equal to m less than n. I was not thinking of negative m. So m is positive, or not, or m could be 0, but it's not negative. And then to make them unique, he imposed the normalization condition, and he just chose Pn of 1 to be 1. And these are called then the Legendre polynomials. And you notice the French have compound names, first names, and sometimes feminine first names, even though they're men. And it's nice to see one of these guys living to a good old age, 33 plus 48. I don't know, 91 or something, or 80, is it 81? Anyway, so let's figure out what the coefficients are. You can figure them out by applying his definition, his two constraints, these two constraints. By the way, here are the first 20 Legendre polynomials. The 0th one is just the number 1. The first one is, the first one is just P1 of x is just x, so that's that line. And then as you go on from there, you get a quadratic, cubic, and I just thought these were really quite remarkable. I just used MATLAB to create these and make the graph. And you can see that they're just quite amusing to look at, I think. The details that are usual in GitHub or GitHub, I've never learned how to pronounce that. And you can find the MATLAB script and so forth. I've been told that I should write a description of what's in each of the GitHub sections, but I have not gotten around to that. I always had something that was more urgent. So, oh hell, we don't want that to happen. As I said, to find these coefficients, we apply Legendre's two conditions, namely that they are orthogonal and that they are suitably normalized. And so one of the exercises to show, excuse me, that this orthogonality condition, that this should vanish for m less than n, you can, this just gives you this equation. The normalization condition is that. You apply these two, and you can see, first of all, the P0 has to be 1, the P1 has to be x, and the P2, well, you just apply these two conditions for m equals 0 and m equals 1, and you find that P2 is 3x squared minus 1 over 2, and then you get P3, P4, okay. Rodrigues invented a really nice formula for the Leibniz, for, I'm sorry, not for the Leibniz, but for the Legendre polynomials. And what he did was he expressed them as the nth derivative of something, the nth derivative of a simple polynomial. And incidentally, this shows you something that I said to you before, namely that differentiation makes things more singular. Because if we go back here, we see that for 0, the formula is just boring. Nothing happens. It's just equal to 1, or it's just equal to x. But as you differentiate successively, you get things that are moving around with considerably more variety, and the derivatives, the values of the functions, they're still between -1 and 1, but their derivatives are anyway, they have much more complicated behavior. I guess I'm not really showing that they're more singular, but anyway. So if you then applied Leibniz's rule, remember Leibniz's rule was, let's see if I can display it here. There's Leibniz's rule. The nth derivative of the product is a certain sum. So that's a sum. This is the kth derivative of the x plus 1 term, and the n minus kth derivative n minus 1. Of course, I'm factorizing x squared minus 1 as x plus 1 times x minus 1. And you can then show that if you apply Leibniz's rule to Rodrigues' formula, you get this, and at x equal to 1, well, at x equal to 1, all these terms vanish, so you could just get this, and that just gives you that, which is just 1. So Rodrigues gets the normalization right. And then if you then apply either one of these formulas, you can, with a little more effort, you can find the higher order Legendre polynomials. And MATLAB will give you the numerical value of any Legendre polynomial by this incantation. Gives you Pn of x numerically. To check that they are suitably orthogonal, well, you just write it this way: x to the m, Pn has to integrate to 0, but Pn is this nth derivative. Well, you integrate by parts n times, but each of this quantity here vanishes at both boundaries. So you drop all the boundary terms, you just get this, and obviously if m is less than n, this thing vanishes. Okay, and you can further show that the integral of the product of two Legendre polynomials is 0 unless n, well, we've already shown that it's 0 if n is not equal to m, but if n is equal to m, it's 2 over 2n plus 1. Now, yes, that is what's on the cover, or at least that's what I asked them to put on the cover. Actually, I generated the cover art. Cambridge gave somebody else credit for it, but it was I was the one who sent them the image of what's on the cover. And the cover, though, because they wanted to use big, thick lines, they could only do the first, I don't know, maybe 7 or 10 Legendre polynomials rather than all 20. Anyhow, one of the magical things in mathematics are these things called generating functions. And the generating function for the Legendre polynomials turns out to be this funny inverse square root. And what you can see then is that Pn of x is the nth t derivative of this funny inverse square root evaluated at t equals 0. And to see that this actually gives you the Legendre polynomials, well, you write the integral of the product of 2 of the generating functions. Well, this is rather a scary integral, but it's a doable integral, and one finds that it's looking in an, I didn't do this integral by hand, I don't think, but I looked in an integral table and found out that, or used Mathematica or something, and this is the answer. And however, we did have, I did show you a logarithmic series for this. Please come up, damn it, it's so unpredictable, the response. Okay, there's the log of 1 plus x over 1 minus x is a certain series, and if you apply that to this series, you get this. On the other hand, the same integral, if you write the generating functions in terms of what we want to be the Legendre polynomials times t to the n or v to the n, and then do the integration, what you get is, you see that the integral over, oh, I'm sorry, you're not doing the integral, you just compare these two things. Now, if you compare these two things, in other words, these two are equal, and so this thing has to equal that, which is this. And so now you compare the coefficients of t to the n, v to the m, and you see that they're non-zero only if n is equal to m. And if you then compare them, you see you get this as the answer. So these are the Legendre polynomials. Sorry, I did the wrong thing here. And if you set x equal to 1, you then find that, that you get g of t and 1 is 1 over 1 minus t, and that's sum of t to the n, and that's got to be Pn of 1 t to the n, and so you get that they're properly normalized. That Pn of 1 is 1, and so these are the Legendre polynomials. So this is the magic formula for Legendre polynomials. And this is something that is, of course, of great use. And in fact, this may explain some formulas that you probably were shown as a sophomore in college. And namely, looking at the Green's function for a static mass 0 field, like that, like an electrostatic field or a static gravitational field, you have 1 over 4 pi r and the distance. And if you write that as big R minus little r, again, I can never think of 2 different letters for something, it's just stupid. Anyway, it's then equal to this, and it turns out this satisfies the minus Laplacian on big G gives you the delta function. And if we set x equal to cosine theta equal to this dot product over the distances and t equal to r over r, factor out a 1 over r, we can take this Green's function and rewrite it successively as the generating function divided by big R. And so our formula for the generating function then is 1 over big R times the sum little r over big R to the nth times Pn of cosine theta. So that's this series rewritten. And so this explains how it is that these static potentials can be expanded in terms of a little distance and divided by a big distance to the nth power, and then a Legendre polynomial, the cosine of the angle between them. So I think that's the most important part of, or one of the most important aspects of this chapter, that is to say, understanding this derivation. Now, Legendre's differential equation, well, Rodrigues's formula expresses the Legendre polynomial as the nth derivative of something, and the something is pretty simple. And so you can then, well, this is sort of technical. We define u this way, and so then the first derivative is this, and you can then see that this first derivative satisfies this equation. You then use Leibniz's rule to differentiate both sides of this equation, which is that equation, n plus 1 times, and then you get this and that, and you equate the two and you get this. So in other words, what we've done here is we've differentiated the simple thing, n plus 1 terms, and the more complicated thing, 1 plus 1 terms, and equating the two and using the fact that the nth derivative of u is related to the Legendre polynomial by Rodrigues's formula, we get Legendre's equation in self-adjoint form. And the differential operator then is formally self-adjoint. The real function p is positive on the open interval. It vanishes though on the endpoints, so the upshot is the Legendre differential operator, his differential equation, the domain D of functions that are twice differentiable on the interval form a singular self-adjoint system. And the Legendre polynomial then is an eigenfunction of this operator with eigenvalue nn plus 1, weight function w equal to 1, and the orthogonality relation tells us the eigenfunctions of, so that orthogonality relation that we derived in general tells us the eigenfunctions of a self-adjoint differential operator that have different eigenvalues are orthogonal on the interval and with respect to the weight function. So in our case, we get Pn, Pm integrated is 0 unless n equals m. The eigenvalues are n plus 1. They increase without limit. And so our discussion of completeness in chapter 7 shows that the eigenfunctions, the Legendre polynomials, are complete. And the weight function is just unity. And so we can use the analysis of 7.38 to show that Pn of x times Pn of x prime summed from 0 to infinity and multiplied by this thing, which just makes them normalized, gives you a delta function. And what I did was I did 10,001 terms in that expansion and got us a nice delta function here. This again is MATLAB. One of the things that bothered me always as a student was that we were always told that the states in quantum mechanics form a complete set and they give you a delta function and the functions gives you a delta function. And I had never seen that actually adequately explained, and so that's why I emphasized it in this book, because I think it's important, and I think we can see it graphically, and it's not that hard to understand. If we multiply both sides by a function and then just use the properties of the delta function, well, this integral just gives us f of x. On the other hand, the delta function is this sum, and so we get this sum here. And this is said to be the Fourier-Legendre expansion of a function. So here we're expanding a function as an infinite series in Legendre polynomials, and the coefficients are given by this integral times this number. What is often done, especially in elementary physics courses, is they never show you x in an elementary course. They tell you instead, they write, replace x by cosine theta and 1 minus x squared by sine squared of theta, and d by d theta then is minus sine theta d by dx, or actually they go the other way. And in these variables, they show you Legendre's equation in this form, which is somewhat mysterious. I always found it mysterious, miraculous, amazing. And you see it's in this form, it's confusing and puzzling and mysterious, almost religious. And on the other hand, if you write it in this form, well, that's entirely plausible. I mean, it could have a polynomial that satisfies this equation. In fact, these polynomials are quite simple, and they're on the cover of the book. Okay, so there's recurrence relations. Well, this is technical, and frankly, I've always found it hard to change variables without making a mistake. The concept is simple, but doing it, especially when integers are involved, and you're not talking about all integers, but you're only integrating from, you're only having integers from 0 to infinity, or even worse, some integer n up to some other integer m. That sort of can be confusing. Anyway, the generating function is this. The t derivative is that. We can rewrite that as this, and then what happens is you then find you've got a recurrence relation. Now there are a million recurrence relations for Legendre polynomials, and one can use them to generate the Legendre polynomials. And so I'm going to sort of, this is just an example. Well, that part was an example, but the x derivative of the generating function is this. You can rewrite it as that, and you equate coefficients of t to the n. You get another set of recursion relations. I don't know. I mean, I think this, they might be useful here and there, but since we have modern computers, I'm not sure we really need to emphasize these recurrence relations. Special values, well, at x equals -1, the generating function has this simple form, which is 1 over 1 plus t, so that's the sum of minus t to the n. So see, this is why I emphasized in the chapter on infinite series examples like this. And so now we see that this has to be this Pn of -1 t to the n. So now we know that Pn of -1 is -1 to the n, whereas Pn of 1 is 1. And G, the generating function, it's even under reflection of both variables, because this one gives you a -1 to the n, that one gives you a -1 to the n. So Gn of Tx is G of Tx is G of -t minus x. G being this, well, G, maybe I should switch. Just to remind you, I think you absolutely know what it is, but let me just switch maybe to blue now. So G of t and x is 1 over the square root of 1 minus 2tx plus t squared. I hope I got that right. No, there's no 2 there. Oh yeah, there is a 2 there. Okay. All right, so since it's even under reflection, you see that Pn of minus x is minus 1, Pn of x, and so the odd ones have to be 0 at 0 because you get a minus sign here. And you can find the even ones with some more effort, you can get this expression for them and so forth. NIST has many valuable, the National Institute of Science and Technology has very useful web pages, and they have all kinds of arcane formulas for various things, which can be quite useful. I think this, for example, is something that shows up in the analysis of the cosmic microwave background radiation. The relationship between Legendre polynomial and zeroth order Bessel function. So let's see, why am I going through all of this? Well, if you have expressions involving factorials, these rapidly become difficult to deal with. And so approximations like this are really quite useful. And so in particular, if you were looking at P20, say, you would have 20 factorial here. That's a nightmare thing to deal with numerically. Schlaefli took advantage of Rodrigues' formula and the work of Cauchy, and just used Cauchy's integral formula to express it this way. So the nth derivative is the counter-integral around x of dz over z minus x, and then you put the function up there, z squared minus 1. And so in other words, this particular equation there, let's see, yeah, I see it's not actually explained. So in other words, this equation, these equations here are that Pn of x is 1 over 2 pi I integral Pn of z minus x dz. Well, that's Cauchy's integral theorem simply. But if you want Cauchy's integral formula, well, what you have is that this is 1 over 2 to the n factorial, and then d by d x to the n of x squared minus 1 to the n. Well, that is 1 over 2 to the n factorial. And now we're saying d by dx to the n of this thing, and that thing is z squared minus 1 to the n over z minus x dz. And on the other hand, this nth derivative there, you can then use Cauchy's integral formula to rewrite it. You get rid of the n factorial and the derivatives. Oh, I forgot the 2 pi I here. There's a 2 pi I here. And so what's left is 1 over 2 to the n 2 pi I, and then you have an integral z squared minus 1 to the n, but now this is z minus x to the n plus 1 dz. And this is any contour. Here's the complex plane. There's the point x. X marks the spot. And so you do an integral, any old contour that goes around that. So that's Schlaefli's integral formula. And it turns out that Rodrigues' formula is much more general than its application to Legendre polynomials. And I never read any of Rodrigues's paper, but I'm certain that he applied it broadly to generate all kinds of families of orthogonal polynomials. And one generalization of that he, I'm sure, developed was that a polynomial R sub n of x, and I'm using R for Rodrigues, is 1 over some constant, a scale factor, W, some weight function, an nth derivative of something, the weight function times the nth power of something simple. And it turns out that if you just use this formula, this Rodrigues structure, these then turn out to be orthogonal on the interval from A to B with this particular weight function, as long as Q vanishes at the two ends. And that's actually an interesting exercise. 9.8 actually. And examples are the Jacobi polynomials, the Gegenbauer polynomials, the Chebyshev polynomials, the Hermite polynomials, the Laguerre polynomials. So all of these mysterious things have Rodrigues type formulas, and their whole structure is exhibited then by the Rodrigues formula, and I think that's quite nice. And I think I really should have a little something describing Rodrigues's birth and death. So let me just make a note to myself that I ought to do that, because I can barely pronounce the name Rodrigues because I never studied Spanish. Okay, so we're out of time, but I'll answer a question if there's a question. Notice that I've been updating on the class webpage the various files, examples, and so forth. And those files that come from the iPad, these files also I just update by continuing to write. So the thing I was doing today is a continuation of what I did yesterday or the day before. All right, well, I'll stop it now if there's no question. Have a nice evening. Be careful over the weekend. Stay out of bars and look both ways crossing streets. Don't get run over by one of those ARC buses. So I'm gonna stop share and end it and